So before I take up this problem, that is the characterization of the diagonalization, let me make some remarks on the example that we have considered. Recall that we did a example for triangulation and how one gets along with it. I want to make a remark. The remark is this, that the matrix representation that you get is not a unique matrix representation. In fact, the very fact, if you examine the mode of working, you will realize that there are several choices for V1, V2, V2. And they are all probably sometimes scalar multiples, or when it comes to choosing V3, you see that it's a linear combination of V1 and V2 that is involved in solving the equations. And there, depending on what coefficients you use, that makes a difference. And in fact, if you recall the computation involved, see, we had some other state, just to go back to the calculations, W2 equal to the span of V1 and V2. Then what we were doing is that A of P of we were searching for P of V3 is equal to an element of T minus lambda I of V3 equal to a linear combination of, that is A1 V1 plus A2, where A1 and A2 are scalars. Now, in the case that we have considered, lambda I happens to be 0. Therefore, we were working on TV3 equal to A1 V1 plus A2 V2, and then finding out the particular V3. So, you had plenty of choice for V3 by choosing different A1 and A2. This is one point I wanted to make. And consequently, the representation T with respect to the ordered basis is in fact, what you can have is this, that on the diagonal you will have only these roots of the characteristic polynomial. So it will be A11, A12, A13 in this case, but here it is going to be 0. And then you see that this portion that you have, these three elements that you get, 1, 2, 3 elements that you have. So these elements are going to be different, and it depends on what you use. This is one. Okay, let's just say just a casual example. Now we give a problem to the triangulation. That is this. Suppose C belongs to and the associated field is an algebraic. These are the sequences. Then what we can say is these Now the proof is very simple. So all that you need to do is observe is that since the associativity F is algebraically closed, the minimal polynomial for B splits into product of so in this case, for example, if you are considering the field C is algebraically closed, and all polynomials with complex coefficients split into product of linear factors. This is the consequence of F being algebraically closed. Therefore, so that implies is to recall that first example where we considered the problem on R when both the characteristic polynomial and minimal polynomial for that operator was lambda squared plus 1, which does not split in R into linear factors. Whereas in C, it actually splits into linear factors. So that's the point. Okay. So this is just a very quick inference from using the fact that using the assumption that this summation. Now we come to the main theme of today's talk, that is characterization. This is what is called diagonalizable. See, let us just recall a few things. We have a dimension of V to the n. The associated field is over the field F. Then we are taking field belonging to now you know that if F is a characteristic polynomial, of E See, let E be the see what we have observed. To recall the three examples. In the first example, if you were to use R as the field, then the characteristic polynomial does not split into the product of linear factors. And in that case, we have seen that it cannot be, you don't get two linearly independent vectors which are eigenvectors of P which spans the space. Therefore, no question of diagonalization coming to that case. Further, if we were to use C instead of R, then we found that you can diagonalize. Now that lambda square plus 1 splits into lambda minus I into lambda plus I. So I get minus I are the eigenvalues, and then you get a diagonal form where the diagonal elements are I and minus I. So that's the first case. In the second case, we had the F. In case 2, we had example 2. We had F lambda equal to so it's although we are working with the R, the characteristic polynomial splits into linear factors. However, in this case, W1, which is the null space of E minus I, is of dimension 1. W2, which is the null space of T minus 2y, which is also of dimension 1. That is the problem. But the vector space has dimension 3. Okay? So W1 plus W2 was properly contained. This is 2-dimensional, this is 3-dimensional. And in that case, T was not diagonal. Now, if you carefully investigate in this case, see that P lambda in this case turns out to be simply lambda minus 1 equal. So then you have got P equal to 0, of course, Pt equal to actually Ft, and it is 0. That's no problem. But lambda minus 1 into lambda minus 2, which probably divides F lambda. If you take G lambda to be equal to this, then G is a possible candidate to be the minimal polynomial, but Gt is not equal. That's the problem. It is not diagonalizable because we didn't get enough vectors, eigenvectors to span the vector space. But in example 3, we had again f lambda equal to but in this case p lambda becomes or in this particular case we were able to show that p equal to. So this case you had the W1 corresponding to eigenvalue 1 is of dimension 1. W2 which is the eigenspace associated with the eigenvalue 2 has dimension 2. Therefore we got enough eigenvectors to span and therefore it was diagonalizable. P is diagonalizable. So it's an observation by playing around with a lot of examples that in the diagonalizable or non-diagonalizable case, you never had p lambda as a polynomial that splits into distinct linear factors. So observation. P is not diagonalizable. Then the corresponding linear formula not split into product of distinct For example, in the example 2, it did split into product of linear factors, but it was not splitting into linear factors which are distinct because lambda minus 2 appears twice. So it is actually lambda minus 1 into lambda minus 2 into lambda minus 2. That is the linear splitting that you can write down. But lambda minus 2 was appearing twice. Whereas in this particular case, it was splitting into linear factors distinctly. So these two are two distinct linear factors. So, what one would conjecture at this stage is that T is diagonalizable if and only if the minimal polynomial splits into the product of distinct linear factors. Now this is a theorem that we want to do. In fact, we found that if you recall the analysis, what we had in the diagonalizable case, let me just recall. See, in the diagonalizable case, just to recall, in the diagonalizable case, you see that so recall our diagonalizability is defined by the possibility of writing V as the direct sum of W1, W2, etc. or W2, where each one is an eigenspace corresponding to some eigenvalue. And in that case, we have directly verified that F lambda is certainly of the form this is necessarily so because you know that you get the matrix summation, it has only diagonal elements. Then you compute the characteristic polynomial of that matrix, which is the same as the characteristic polynomial of the operator. So it can only be in this particular form. So a necessary condition for diagonalizability is that is a necessary polynomial splits into then we have seen from the example 2 that this condition is not satisfied. It's not satisfied. When we carefully examine the examples in our hand, we looked at the event to consider the minimal polynomials. We observe that in our examples, splitting between distinct equilibriums. So the natural problem was, and we also observed the other part. Whenever it did not split into distinct linear factors, we had non-diagonalizable. See, this is the observation. Also observe that in the case of examples, non-diagonalizable. Let us the linear polynomial fail in distinct linear factors. These are all observations. So the question that you ask at this stage is, does there exist necessary condition for explanation of this question and trying to build a proof in the general case. Let me the following characterization is known to us. So we write it as is distinct eigenvalues. So P lambda is equal to so let us do this. So we will be making some conductor etc. What is this guy? This guy is this. One part is what we have already seen. Assume T is diagonal. The characteristic algorithm then we have proved that was here the distinct zeros of f lambda both P is an even polynomial we have the solution here. Which implies P lambda is of the form if where 1 this. have shown that if I then we prove that G lambda defined by that is the case if R1 equal to 1, R2 equal to 2, etc. R3 equal to K has the property therefore G is an annihilating polynomial. That is under diagonalizability we are able to do this. So with the assumption that B is diagonalizable, we were able to do this. Therefore, Therefore, no polynomial of less than that of P which implies G is P. Hence R1 equals 1. Okay. So the earlier proofs we fall upon and then so this is what you already done. It's just information together. Now come to the difficult part, namely that if P lambda is then P is there. What's the answer? So the method of proof is the following. Say contrapositive. Suppose T is not diagonalizable, then P lambda cannot have this concept. So we use contrapositive. Assume P is not bad. Then we show that now. That means what we want to say is that there is some lambda minus lambda j appearing with multiplicity more than that. Okay, so we will proceed with that. So let us see. So we have assumed P is not diagonalizable. So P not diagonalizable. The subspace W span from eigenvectors of is a proper that is W is not equal to W span by eigenvectors. Therefore, this is an equal covers a part of this. Now we can use that econductivity. This. And a characteristic value of the such that the operator that works is E minus and this is the operator that works. So that carries it into W. Now W is essentially it's a unique breakup of W because W belongs to W. It's a unique sign. And this is true for 1. Now for any polynomial, H become into we have because of this. What does this mean? It's lambda 1 okay. You see the so use this and then work to H and so on. Okay. And you see that HT for F3 so that property is there. Now let us compute. we take this particular one. So P lambda minus lambda G sum that comes from its form which is, because we know that lambda J is a 0 that's polynomial and the other exists. So, suppose you look at this one. See, this is a constant. Q lambda J is a constant. Whatever you have. Q lambda is. So, this has a property that suppose I call this some. And you see that G lambda J 0. That is clear. Okay? Therefore, which implies G lambda is of the form but G lambda is this. This is the one. Or we shall write it in that form, that is Q lambda minus Q lambda J. This is the one that we are going to use. Now you see that Qt this is equal to, because it commutes I can write it like this, U minus and this is essentially B minus lambda B is what we have defined here. But B minus lambda J B is the B. Okay? So this is equal to it's the definition of the okay. Now 0 equal to Pt. Why Pt is 0? The reason is Pt is an irregularity polynomial and this is equal to P minus lambda Ji Pt. Therefore, what we infer? We infer that Qt in B is an eigenvector of P belonging to lambda equal to. Now UTV is not equal to 0. Why it is not equal to 0? Because degree of P is strictly less than P is a minimal polynomial. But what this is, so this is not equal to 0. Therefore, to see that this is an eigenvector belonging to the eigenvalue lambda. What is the implication? This implies therefore we have a few things now. QTV belongs to W, HT W certainly belongs to W. Okay? Therefore, from this one, we have QTV is in W, this is also in W, therefore it's anyway in W, W is in capital W. Any polynomial of W is. So Qj, Q lambda j, but V does not belong to, so this is a scalar. And V does not belong to W. And that forces Q lambda j what does it do? This implies lambda minus Q lambda is equal to some power. Okay. What is the implication of that? That means lambda minus lambda j square is now a backdrop. Least 2 is quadratic. It's the product of this two video. So that's second. So that is the proof of the. So finally, we got a characterization of diagonalizability in terms of the structure of the graph. This characterization. In terms of so that's a beautiful theorem which characterizes diagonalism. Something I'll stop. Thank you very much.